Okay, in today's video, we're going to talk about plumbing gas riser diagrams. So we're going to first discuss the relevant code sections on gas piping in New York City. Then we will go over the units used in gas flow and common conversions used in gas piping design. And then we're going to discuss two methods of gas pipe sizing, followed by an example will then be shown where the gas rise diagram will be designed using the gas piping shown on the plumbing plans. And this is how a typical gas meter setup will kind of look like. You'll see a header, which is the main pipe, typically the same size, that then taps out into the individual gas meters, which you see here. And what's below here is probably another set of gas meters that are cut off around this area. And this right here is the valve. And usually there's a lock on the valve by the utility company so that if somebody doesn't pay for their gas, they can actually shut off the valve and lock it out. So the gas piping code regulations are covered in the New York City Fuel Gas Code 2022, Chapter 4, and this is the current version at the time of this recording. So if you go here, you could just type in a search for New York City building codes or the fuel gas code, and you'll see this come up. This is the URL here. Under the fuel gas code, Chapter 4 is basically the section that deals with gas piping installation, which is here. So some of the relevant units and conversions that are used with gas piping is a term called CFH, okay, which stands for cubic feet per hour, and this is the volumetric flow rate. So the volume is here, and it's per hour. So this is the volumetric flow rate that's typically used when talking about gas flow rate. You also have BTUH, which stands for BTUs per hour. This is a unit of heat energy. And 1 MBH is just 1,000 BTUs per hour. And 1 MBH is actually equal to 1 CFH. So 1 cubic feet per hour converts to 1,000 BTUs per hour, which is basically this right here. 1 MBH is equal to 1 CFH. Next common unit used is inches, WC, which stands for inches of water column. And these are the units that are used to represent the amount of pressure in a gas system. And this pressure of whatever inches of water column it is the actual pressure of the system. Meaning if you have 2 inches of water column of pressure in a gas pipe, it represents that it has the equivalent amount of pressure as 2 inches of water column. So the units actually represent exactly what the pressure of that gas system is. Okay, and the next is 1 psi, which stands for pounds per square inch, is equal to approximately 27.7 inches of water column. So whatever pressure is at the bottom of 27.7 inches of water is equal to 1 pound per square inch. And the conversion between feet of pressure to psi of pressure, you just divide it by 2.31 to make that conversion. This is just a general setup of the service. So the service comes in here, okay, and then you have the shut-off valve here, which typically has that lock from the utility company, and it goes into this meter. Sometimes you'll see this, which is a PRV, pressure reducing valve. Here is labeled as gas regulator. They mean the same thing. And what it does is it reduces the pressure to a specific pressure that is allowed by the code. So the code doesn't want such a high gas pressure to exist in a building, for example, like a residential building, because you can have a lot of gas leaking into the building if there is some sort of crack in the pipe. So they want to limit the amount of pressure that is inside of a building. And you do that with this PRV or gas regulator. Then it goes basically into the meter, and it then goes into the house. This is a sediment trap, and this is what a gas valve looks like. A valve used on gas piping is referred to as a plug valve, and this is what it looks like. So it comes in here, and then you see here, this is a union. So this union basically will just slide in and out, and you could basically remove this pipe from this pipe through this union without having to move the piping or the equipment to basically disconnect these two pipes. Now, if you didn't have this and it was just a solid pipe, to remove this pipe, you may have to bend this pipe backwards or move this equipment so that you could have spacing to unthread the pipes. So the purpose of this union is to make a connection and also to remove it without having to move any pipes or equipment to separate that connection. So here are the labels. This is a plug valve. The piping used for gas is typically black steel pipe, and it looks like this here. This is the sediment trap, and this is the union. In this picture, this is actually looks like a water heater. For equipment that moves, if it has wheels or it can be basically easily moved, the gas piping is connected through a flexible connection, which is represented by this yellow piece here. And this flexible piping has to be UL listed for use in whatever area that you are in. And this wire here is connected to the wall, and this basically restrains the equipment from moving too far of a distance that may cause this flex connection to break. Alright, so sediment trap shall be installed to collect sediment downstream of appliance shutoff and close to the inlet of appliance. And some of the exceptions are ranges, clothes dryer, fireplaces, and outdoor grills. And this is the code section, 408.4 of the New York City Fuel Gas Code, which is right here, 408.4, this section right here. So if the gas is coming down this way to the appliance, the shutoff valve will be right around here. So going back to, let's say, this picture here, this is the shutoff and this is the sediment, so it's downstream. Downstream means basically in the direction of the gas flow. So if gas is going this way to the appliance, downstream of the valve would be this section here, and upstream of the valve would be up here. So the sediment trap would be downstream of this valve, closest to the appliance. And this is required by code. And the exceptions are these things right here. So just going over some of the terms, if you look on the right here, the range is basically a cooktop, which is this piece right here. And then the bottom piece of that cooktop is the oven. So when you combine the cooktop and the oven all in one piece, it's called a range. And if you just have a cooktop right here and no oven below it, it's just called a cooktop. And an oven by itself looks something like this. So a range is a combination of both the cooktop and the oven all in one piece. So a range would be an exception to the sediment trap. Now, gas piping is sized based on Table 402.4 of the New York City Fuel Gas Code. And that Table 402.4 is right here. So this is basically the charts that would be used or could be used to size gas piping. So in New York City, Con Ed and National Grid supplies gas to the buildings. They basically represent different areas. So National Grid will supply gas to Brooklyn, Staten Island, and most parts of Queens. And Con Ed would supply gas to basically New York City, Bronx, and some parts of Queens. The utility companies provide 4-inch water column of pressure is the minimum supply that the utility companies would provide at the outlet of the gas meter. So going back here, the outlet of the gas meter would be right here. And the utility company would provide a minimum of 4 inches of water column of pressure at that point. The max inside gas pressure is not to exceed a half psi based on section 402.6 with some exceptions. And here's the section 402.6, and it states here the maximum design operating pressure for piping systems located inside buildings shall not exceed a half a pound per square inch of pressure. And there are some exceptions here that you can read on if you want to get a better understanding of the different exceptions here. So if you have if the gas service here is providing gas exceeding half a psi, you have to reduce that pressure within the building to not exceed a half a psi. So half a psi or less. And to do that, you would then need this PRV here to reduce it to half a psi or less. So that half a psi would basically convert to approximately 13.8 inches of water column. So that half a psi to approximately 13.8 inches of water column came from this conversion here, where 1 psi is equal to approximately 27.7 inches of water column. So we're now going to talk about the gas piping and where it is allowed to be installed, and basically it's allowed to be installed anywhere except for the areas that the code prohibits gas piping. And that section is 404.3, which I took a snapshot of and I pasted it right here. And if you want to get the full codes on that section, you could just go to the fuel gas code and go to 404.3, which is right here. Section 404 and 404.3 would talk about the prohibited locations. So just to quickly list some of these locations, you cannot put anything through any ducted supply, return, or exhaust duct, which should be obvious. You don't want any gas leaking into the HVAC system and distributing throughout the building. You cannot put it into trash or closed chutes, chimneys, gas vents, dumb waiters, elevator shafts. So you can't install gas in these areas here. So stair enclosures, fire standpipe riser. Fire standpipe is generally the things that you see with the hoses attached, or maybe you'll have a valve without the hose attached. So if you just do a search online for fire standpipe, this is what a standpipe is. So it's generally just a riser with a valve connected to a hose. Sometimes it doesn't have a hose and it just has a capped valve such as this here or here. So you can't put it in any shaft that contains a standpipe riser. You're not allowed to put in fire pump or fire pump rooms, as well as fire rated construction. So gas piping shall not be installed within a wall or assembly required to have fire resistance rating. Also, you are not allowed to put it in public corridors except if it follows any of these exceptions below. Also, you cannot put it in solid partitions and walls unless installed in a ventilated chase or casing. Now, if you look at this section, past all the areas where they prohibited gas piping, they also explain, how to install the gas piping if it is basically installed in different areas, such as in solid floors, where one end is terminating outdoors, conduits with both ends terminating indoors or above ground outdoor piping. And this section basically provides how to protect the gas piping against corrosion if it is in soil or just exposed to exterior locations. So if you want to learn more details on these items here, you could just read through this code section here. They also discuss the minimum burial depth, which is not less than 24 inches, 24 inches below grade, measured to the top of the pipe. So you could read this section to get a better understanding of these things. Okay, for plumbing gas pipe sizing, there are two methods that are mainly used, and one is the longest length method, and the other one is the branch length method. For the longest length method, if you look here, this is basically the point of delivery, and the gas will basically flow to all the different outlets that you see here, outlet C, D, B, and A. This is, for example, a clothes dryer at 35,000 BTUs per hour. This is also equal to 35 MBH, and also it is equal to 35 CFH as well, cubic feet per hour of gas. So these all mean the same thing. They are all equal to each other. And when you size things based on the longest length method, you want to find from the point of delivery here to the furthest fixture. So if you follow the sizing here, this is 20 feet. This section is 20 feet. Here we got 10, here 15, and here 5. So outlet A would be the longest length from the point of delivery that we see here. And that distance is basically 10 plus 20, 30, plus 10, 40, plus 15, 55, plus 5 is 60 feet. So this distance of 60 feet is the longest length in this system here. And this will be used to size every single pipe segment that you see here. So this would be one segment here. This would be another segment here. This would be another segment here. And for each segment, you sum up the total CFH. So for example, outlet A is 35 CFH. This outlet B would be 75 CFH. So the total of 35 and 75 would be 110. So here it would be 110 CFH. And this segment here would be the total of everything, right? So you would have 110 plus this this outlet, which is 100 CFH. Here would be 35 CFH. So the total here would be 135. And the total for section 3 would be that 135 plus the 110. So that would be 245 CFH for section 3. And we would basically use the chart to size the piping. So the gas piping is sized based on table 402.4. So we're going to go to that table. So here's the table 402.4, and it's going to be this one right here, Schedule 40 metallic pipe. Schedule 40 just represents the thickness of the piping. Okay, so here we have natural gas, that's correct, and the inlet pressure is less than 2 psi. And usually the case is 4 inches, about 4 inches of water column pressure at the gas outlet. All right, so the service pressure is going to be about 4 inches of water column. So if you go to this conversion again, 2 psi is over 54 inches of water column. And since we have 4 inches of water column at the outlet of the gas valve, we are under this 2 psi. So this table can be used. The pressure drop maximum is going to be 0.3 inches of water column. Okay, and this table is based off of this pressure drop. So what this table shows is, for example, a 1-inch pipe size and the length is 10, you can have 514 cubic feet of gas per hour, or CFH, up to that point to get a max pressure drop of 0.3 inches of water column. So let's say going down this column here for 1 inch, if we have a higher length of that 1-inch pipe, let's say 20, the maximum CFH is less because now you have a longer distance. So if you had the same amount of gas flow and the pipe is longer, you're going to have more of a pressure drop. So to maintain this maximum 0.3 inch water column pressure drop, the CFH has to be reduced as the pipe length increases for a given pipe size. So let's say you have the same length and the pipe size increases. As the pipe increases, you are able to carry more volumetric flow rate, right, more CFH, and still maintain that max pressure drop of 0.3. Okay. So going back to our example, for this longest length method, we have to use the longest length of 60 feet for every pipe section here. So we're going to first size this main section here, okay, the one that has a total of 110 plus 135, which is 245 CFH, and the distance will be 60. So if you go here, we find the length is 60, so they have one here. Let's say the length was 65, then you would just assume a longer length, and we would just use that length. But in this case, we have exactly a 60-foot length row here. So we're going to use this row here and go across and find something with 245 CFH. So we go across here. This is too low. This is the max we can use for a 1 inch. But for a 1¼ inch, we can go up to a max of 400 CFH. So we could size that section as 1¼ inch since it's below this maximum CFH amount. Okay, so this will be 1/4 inch. Now let's size section 1. And section 1 has 110 CFH. So again, we have to use the same length for every pipe segment. So we got to follow this 60 again, which is the longest length, and find one that can handle the 110. So 110 would be this one right here, which is a 1 inch. So this one would be a 1-inch pipe size. This section 2 is carrying 135 CFH. So 135 CFH running across the 60 foot row. Would be a 1-inch. So this would be a 1-inch size. And you would basically do that for all the other sections. So let's just do it anyway. So this section here, right, going to outlet B is 75. So 75 would be 3/4 inch. And the pipe going to outlet A is 35 CFH. So going across 60, 35 would be 1/2. So basically here we sized all the pipe sections using the longest length method. We also have to size this pipe here, which is for outlet D. They didn't actually give us a feet distance here in this diagram, but let's say it's about, 5 feet or so, right? So then this would be 25 feet, and this 60 feet would still be the longest length. Now, if this was this pipe section here to outlet D, from here to here was, let's say, 100 feet, then the longest length would have to be starting from outlet D to the point of entry. But in this case, the 60 feet, let's just say, is still the longest distance. So that size to outlet D would be 100 CFH at 60, so it would be a 3/4 inch here. So we basically sized all the pipe segments using the longest length method here. Alright, now we're going to go over the branch length method. So for this method, section A would basically sum up all the CFH for all the fixtures that's running through that pipe. So it would be a total of 20, 30, and 60, which is 110. So here it would be 110 CFH. And each of the other sections would be sized just with the CFH going to that fixture. So section B would just have 60 CFH, section C would be 30, and D would be 20 CFH. And the length that's used would be basically the longest distance for section A. So the longest distance would be the furthest fixture to the gas meter here. So in this case, section B is 15 feet, section C is 10, and D is 25. So the longest distance would be from the emitter to the fixture going through section D. So D is 25 feet plus A, which is 125 feet. So this 125 feet would be used to size section A with 110 CFH flowing through that section. Now to size each individual gas piping to the fixtures, you have to use, instead of the longest length of 125, you use the length of basically that section here plus section A. So for section B, it would be the 15 feet plus the A distance of 100. So it would be 115 feet would be used in the table with 60 CFH flowing through it to size the pipe to section B. For section C here, we would use the distance for C, which is 10, plus the A, which is 100, and this one we would use 110 feet with a a 30 CFH volume flow through that 110 feet of pipe to size basically that section C. And you would do the same for section D, which is 25 feet, plus the 100 feet for A, that would be 125 feet, with 20 CFH going through that section to size the pipe in section D. So if you compare the longest length method to the branch length method, the longest length method gives you larger pipe sizes to the pipes to the individual fixtures because you're using a longer length than what is used in the branch length method. So for example, for section B, we used 115 when the longest length is actually from section D, and that's basically 125 feet. So if we size section B using the longest length method, we would size it for 115. It would be 125 feet. And if you look at the chart, the longer the pipe length, right, for a given CFH, let's just use pick a random number. Let's just say for 10 feet, and let's say 250 CFH, we would use 3/4. But 250 CFH with 100 feet of length would basically give us a size of 1 1/4. So you could see that for a given CFH, the longer the length is, the bigger the pipe size has to be. So the longest length method would just give you a more conservative pipe sizing, since we would oversize some pipes compared to using the branch length method. So this is the method that we should always use as, a standard, in my opinion, rather than the branch length method. Okay, this is another documentation with a gas piping chart. The difference here would be that they give this section here for the riser sizing. And the riser is basically the vertical gas pipe. So if you look at this example here, these represent the floors. The riser would basically be this pipe right here, which is shown as size as 1 1/4. So to size that riser, before the example that we went over is sizing the horizontal branch lines. But to size the riser, which is the vertical gas piping, you use this table here. And you could see the CFH is on this top row, and the pipe size is right below that. And you can see in this table 3 for the riser sizing, they leave out the total feet. So they're neglecting the length of the gas piping when sizing the riser. And the reason for that is because, let's say you have a gas pipe here, and then you have an outlet through one floor, you have an outlet through another floor, and let's just say this is your piping, and it goes out to another floor up here. So let's say this is the the first floor. This might be the 10th floor. This might be the 100th floor. Okay. The reason why the length is not involved in sizing that riser is because gas, which is flowing through this pipe, is basically less dense than the air. So let's say outside of this pipe right here, the air pressure is whatever it is. It's ATM, let's say, atmospheric pressure. And inside is whatever gas pressure you have, right? So you got the gas pressure here. Okay, and since the gas pressure is less dense, as you move up, right? And when I say less dense, it's less dense than the air. So as you're moving up, you're losing pressure in the gas. But then for the same height difference, you're losing the pressure of the air. And since air is more dense than gas, which means that the gas is basically floating. It's more buoyant than the air, right? Because the gas is less dense than the air. So as you're moving up, the pressure for the air is dropping at a quicker rate than the gas. So as you're moving upward, okay, the drop in the air pressure will be faster than the drop in the gas. Okay, so let's say, for example, at floor 1, I'm just making up a number. Let's say it's 10 psi here. Okay, for gas, I mean for the air here. And let's say inside for the gas, it's let's just say it's 15 psi. And obviously this number is quite high for gas pressure, but I'm just making up numbers just to show the net difference between the gas and outside the gas piping. So if you go to floor 10, okay, the drop is going to be faster. So let's say the drop is 5. So in this case, it'll be 5 psi at this point. And the air is going to drop faster than the gas. So if it dropped 5 for the air, let's say it drops 1 for the gas. So here it would be 14 psi. So the difference at floor 1, the gas is 15 and the air is 10. So that's a difference of 5, okay, between the piping and outside. So the outside could be to, let's say, a water heater or a range, right? So you have a pressure difference of 5 here. So you have 5 psi of gas pressure to the equipment that is connected to. At floor 10, we're going to get a difference of 14 and the 5 psi. So now you have a difference of 14 minus 5, which is 9 psi here. So as you can tell, the psi actually increased as you went up. So now here you have 9 psi of gas pressure to your fixture. So as you can see, due to the difference in density, you're actually getting a increase in gas pressure to the fixtures as you're moving higher up, because there's a difference in the rate of pressure change between the air and the gas due to the difference in density between gas and air. And you actually do have a friction loss through the vertical pipe also. And that's why if you look at the chart, you'll see for specific sizes, the CFH, there's a maximum CFH given for each size. And that'll account for the friction loss. So instead of, let's say at floor 1 being 5 and floor 10 being at 9 psi, because of the friction loss through here, rather than 9, you might get something like 6. So it's going to be a little bit less because of that friction loss. And that's basically how you size the vertical section of gas piping. Now there's also a different chart that can be used for gas piping, and it's this chart right here. So on the x-axis you got the gas volume in cubic feet per hour, and on the y-axis you got the pressure drop in inches of water column per 100 feet of gas pipe. So if you look at the top, let's say for a 1 inch and let's say a 200 CFH, you have approximately 0.7 inches of water column per 100 feet of pipe loss. So using this chart, you can get a more accurate friction loss based on the CFH that is flowing through that gas pipe, rather than all these other tables that just gives you a kind of like a range. So for example, it just says up to 199 for a 1 inch, and let's say this 45 feet row, and it just gives you these main kind of ranges for a CFH value that will give you a maximum loss of 0.3 inch of water for that entire uh, pipe length that's shown on this column here. So this chart could be used to basically get a more precise friction loss in the gas piping for a given CFH volumetric gas flow rate. Then these type of charts, which basically just gives you a range of CFH values that would basically lead to a max pressure drop of 0.3 inches for that given feet. So this could be used for more precise calculations of the friction loss in the gas piping than these type of charts. So now we're going to go through an example gas plan, and we're going to generate a plumbing gas riser diagram from that plan, and then we're going to use all the concepts we learned to size the gas piping and lay out the entire gas riser diagram. So let's get into that example now.